Hello and welcome back to the workshop. I've dashed out just now in between rain showers so it won't be deafened by the noise on the roof. We saw in the last video that although respiratory deaths, or deaths from underlying respiratory causes, were at an historic low in England and Wales, the total figure for all deaths in England and Wales was at an historic high. We're going to have a look more closely at why that's the case in this video. We'll use mathematics that are a couple of centuries old to investigate what happened, particularly in quarter 2 of 2020, and explain why it probably won't happen again for a very long time, at least not from the same cause. We're going to finish up, you know how I like charts, we're going to finish up with probably the most frightening chart I have ever seen. We'll take a quick run through some of the charts in the previous two videos just to remind you what we're talking about. This first one is the cumulative respiratory deaths in England and Wales from 2010 to week 42 2020. Week 45 data is now available and we'll revisit this again in a few weeks, but it's not significantly different from this. You can see that 2020 has the lowest number of respiratory deaths of any year in that period. But when we look at the next chart, cumulative deaths from all causes, we can see that 2020 is in fact a very bad year, and there have been significantly more deaths this year than we would have expected, and that's shown by the red line above all of the others but running parallel to them for most of the time. And that was caused by the peak of deaths between weeks 12 and week 23 in 2020. That's quarter 2 in 2020. All of the excess deaths shown in the previous chart have come from this period and from no other. The week 45 data is now in for this as well, and it's showing a slight uptick now, but I'm not entirely sure why that is, and I need to have a good look at the underlying data for that. We can see this effect of this excess deaths much more clearly in this chart, where I've split out just the 2020 data, so we can see exactly what happened in the year. We need to have a little bit of background now on statistical distributions, so I can explain really what's happened in the previous chart. This one that's showing now is what most people think of when they think of a statistical distribution. This is an example of the Gaussian distribution. It's very confusingly also called the normal distribution. So when statisticians are talking about the normal distribution of data, this is the shape they're talking about. It's not normal in the way that normal people use the word. This is a Gaussian distribution. It's named after a chap called Carl Friedrich Gauss, who lived around the turn of the 18th to 19th centuries. The equation for the distribution can be seen in the top right hand corner of this, but it's a very simple, very standard kind of distribution. When Boris was talking about squashing the sombrero at the start of this panic, this is probably the shape that he was thinking of. Somebody has tried to explain to him statistical distributions, and they've shown him something like this. And they've shown him the peak. I would imagine the one they showed him had a much steeper peak, a much narrower standard deviation than this one, and explained that to cope with the demand, the expected demand, they would need to lower the amplitude by squashing the sombrero. They didn't explain to him though that it doesn't actually make any difference to the total number of people that would be affected, it just changes the maximum demand. So that's the Gaussian distribution, which is the most familiar type of distribution to most people. The next ones are several types of Poisson distributions, and these show asymmetric distributions. Gaussian distribution is always symmetrical. Poisson distributions are not. You can see they have a quite different formula, again top right hand of the chart. This type of distribution was described by a chap called Simeon Poisson, a Frenchman, again, who lived around the turn of the 18th to 19th centuries, a period of great discovery in mathematics. But you can see that just by changing some of the parameters in the formula, you can get very different shapes of graph. Although they all go up and they come down. And that's the basic property of these things. One that we're really interested in though is this next one. And this is an example of a Gompertz distribution. Gompertz, you won't be surprised to hear, lived around the turn of the 18th to 19th centuries. And despite his name, he was English. When I was looking for a sample Gompertz distribution to show you, to let you see the type of chart it is, with a very steep increase at the start, and then a long slow decline afterwards, I just flung some parameters at the formula, and pretty much this was the first shape that came out. Rather fortuitous as it happens, and you'll see why in the next 2 or 3 charts. Right, let's go back to real data again. This again is the 2020 data, the 2020 only data. But what I've done is I've started to smooth out the bank holiday reporting anomalies towards the end of Q2. These are the May bank holidays, and they always affect reporting. So what I've done really is just interpolate some of the data, just move it around slightly to smooth the graph off to what is probably more like the real situation in the real world. And you can see here that this is what it looks like. And if you've been paying attention, you'll have seen that shape very recently. Because when I take the curve from the Gompertz distribution sample graph and overlay it onto the data, the actual death data, you'll see it fits pretty well exactly. This is entirely accidental. I did not design the Gompertz distribution to do this, but it just does. It just lies one on top of the other, almost perfectly matching. This demonstrates that the behaviour of the virus in Q2 behaved exactly the same way as every other virus does. It attacked the population. It got a bit of a hand by the fact that the care homes were seeded with infected patients. So the virus had a large reservoir of candidates to infect, and it took the opportunity. But you can see within a few weeks the long tail started to appear, the decay was quick, and the long tail of decay has now kicked in. But you can see by week 26 or so, beginning of June, no more infections occurred. No more deaths were occurring. So at that point, it looks very much to me as if the virus had become endemic at that stage, and there would be no more large-scale infections. And so far, I think that's the case. Despite the uptick that you'll see later in that graph, that looks to me as if it's just normal seasonal increase. But we'll investigate that later. And that's exactly how viruses behave. They attack the easiest candidates for infection first, which is where we see the fastest growth. Then the rate of increase slows down as fewer and fewer people are available for infection. Eventually, very small numbers of people are infected, but the virus never really dies out, it just hangs around. Eventually it becomes endemic, which means that it forms part of our epidemiological landscape, along with hundreds of other nasties. Always there, but very rarely significant. The shape of the long tail can be changed if new candidates for infection become available. For example, if a previously isolated population is infected, but each new infection will take its own form of the Gompertz curve. Over a large geographic area, the shape may not be obvious, but a large population of infections will usually be composed of a group of Gompertz-like curves, each with its own parameters and slightly differing profiles. That's what viruses do. It's been known for a very, very long time, which is why we're describing it with mathematics that are a couple of centuries old. And that makes this next chart that I'm going to show you utterly inexplicable. This chart was presented by Sir Patrick Vallance, Chief Scientific Advisor to Her Majesty's Government at the end of September 2020 in a press conference along with Chris Whitty, the Chief Medical Officer, as the political case was being prepared to shut the UK down again. This is 3 months after I reckon the virus had basically run its course and had become endemic, a background nuisance, nothing more. During the presentation of this chart, he took very great pains to insist that this was not a projection, just a scenario. But it bears no relation to any kind of possible reality. We've seen in the Gompertz distribution what a virus behaviour looks like. This chart shows an exponential growth. It's got no relevance whatsoever to the way that viruses behave. There is no useful information imparted by this chart. I think there could only have been one possible purpose to this presentation, and that was to scare an uneducated populace. It seems to have been very successful. In fact, it's difficult to think how it could have been made any scarier.